All right, everybody. So I wanted to go over the example problem that we did in class with a little bit more detail, a little bit more time, and kind of go over the problem-solving technique and able to just hit everything that needs to be hit when you're going through these types of McCabe-Thiele diagrams. So it's the exact same problem. I have the problem description up here, and I have the diagram right here off to the left. So as I said in class, the first thing that you can do is you're going to have, so you'll have your feed line, you'll have your top operating line, and then you'll have your bottom operating line. Okay? You can plot these in any order. For this, we'll go with what we did in class, but we'll start with the top operating line first. So if we do the top operating line, what you can do is you can imagine a mass balance around the top here, where you have vapor coming in and stream coming out, so that would be V, this would be L. So if we do a balance around the top operating line, which I'll say here, you'll get that with your overall balance, you have vapor coming in is equal to distillate coming out and liquid coming out. Your most volatile is going to be your Vy is equal to your dxd plus your Lx. Okay. From there, we can say that solving for y, we can say y is equal to d over v x d plus L over v x. Rearranging this, we can say that y is equal to L over v times x plus our d over v xt. Okay. From there, we can figure out, we can plug in for either our d or our v or our L with our equation right here. Another thing to note is that we have our L over D, so we're going to want it in terms of either L or D so that we can use this relationship to solve. So if we say L over D is equal to 5/3, then we would want it in terms of L and D, so we would want to get rid of these V terms down here on the bottom. Make it easier because we know we have L, we know we have D. So by plugging this V into this, we can get y is equal to L over D plus L times x plus d over d plus L xt. Okay. From there, if we want, because we have L over D as a number, what we can do is we can then factor and be able to substitute from there. And we can say that y is equal to, just dividing this by 1 over d by 1 over d, we get L over d over 1 plus L over d times x. Plus, and if we do the same thing here, divide by d both sides, we get 1 over 1 plus L over d xt. Now we could just simply plug in for our L over D that we have and say y is equal to 5/3 over 1 plus 5/3 times x plus 1 over 1 plus 5/3 xt, which again we know what xt is. So now at this point we can figure out what our top operating line equation is going to be. It's going to be 5/3 over 8/3 times x, which this the thirds just cancel and we end up with 5/8 x plus, this is going to be 1 over, this is going to be again 8/3 again, and if we just take that, it'll be 3/8 times xt. Okay, so what we have is our top operating line equation. If we want, we could put it in terms of decimals and say that y is equal to this right here. Okay, so that's our top operating line, so we have that already. Next, what we can do is we can go to our bottom operating line. So if we say we have our bottom operating line right here, so bottom. If we do again the mass balance into the mass system, it's going to be our L bar. Out of our mass balance system is going to be our B and our V bar. Similarly, with the most volatile component, we have that it's going to be L bar times XL bar plus B times XB plus V bar times our Y V bar. That's going to be an equal sign. Okay. From there, we can substitute in, plug back in, and we can get a bottom operating line equation in terms of our y bar. So we can say y v bar is equal to L bar over V bar times our x L bar minus B over V bar xB. So if we want to, we can, if we're given our boil-up ratio, we can solve this. If it gives us a ratio or some type of relationship between our L, B, and V bar, we can figure out what that is. However, without knowing what that is, we would have to get a little creative with our solving process. One thing that we can note is from the Q line, our feed line, we know that Q is defined as L bar minus L over F. So if we rearrange it, we can say that L bar is equal to Q times F plus L. So if we figure out what our Q is, we can then come back and substitute in for that. And there's another equation that we can do that can solve for our L bar over V bar. A lot of derivation that I'm not going to get into, a lot of substitution, but our L bar over V bar can then be equal to L naught over T, which is just a reflux ratio, times Z minus XB plus Q times XT minus XB. It's XB. All over not over D times Z minus XB plus Q times XB, that's XD minus XB minus XD minus Z. Okay, this comes in with some substitution and some rearranging. However, we're just going to use a much simpler process and skip for now and focus on our feed line. So if we focus on our feed line, we have a couple of definitions for our feed line. The main one involves either Q or F. However, we know that Q is defined as L bar minus L over F, which is the change in the liquid composition when the feed enters the system divided by the feed flow rate, which can be equal to our enthalpy differences. And I'll explain what these are here. So this HF is the enthalpy of the feed at the temperatures that it's given and the conditions that it's given. So if it's a two-phase, you would have to go to an enthalpy diagram and go to the two-phase system. If it's subcooled or superheated, you would have to go to whatever the corresponding enthalpy is there. This enthalpy is the enthalpy of the feed if it was a saturated vapor. And these are the same enthalpies here. These are the same. So it's going to be a saturated vapor line. You go to that enthalpy and you read from there. This would be the enthalpy of the feed if it was a saturated liquid. So one thing I wanted, so you would go to the saturated liquid line for this one. One thing to note is all of these assume the Z concentration. So that's your HZ, that's at HZ, and this is at HZ as well. So all of these are going to be determined from the concentration of whatever your feed enthalpy is. Okay. We also have that our feed line equation in terms of Q is equal to Q over Q minus 1 times X plus 1 over 1 minus Q times our Z of our feed. There is an equation that relates it in terms of little f, which is our fraction vaporized. However, we're going to use Q because Q we have a definition on how to find in terms of enthalpy and in terms of liquid flow rate. But if it does give you fraction vaporized, you can use the version of the feed line that uses little f. So we know from here, if we want to plot the feed line, we need to figure out what our Q value is. So to figure out our Q, we need to use our enthalpy right here. Because it gives you temperature in the problem statement, that's a good indication that you will need to use enthalpy here. So it gives it that the temperature of the feed is 80 degrees Fahrenheit. So let's then use an enthalpy table to figure out what that's going to be. So we were given the temperature of the feed is equal to 80 degrees Fahrenheit, and the Z of the feed is equal to 0.2 mole %. Here's where you have to look at what's given here on the table. So we're given degrees Fahrenheit versus all of these are in Celsius. So we need to convert to Celsius. You can just Google or do a conversion, and you get that this is approximately equal to about 26.7 degrees Celsius. To convert mole % to weight %, you can just assume that they use the molecular weights of each component. So in this case, we have ethanol and water. So the molecular weight of ethanol, and then the molecular weight of water. And you can assume a 100 mole basis and then go from there. So for example, the molecular weight of ethanol is OH. You have 2 carbons, 3 hydrogens here, 2 hydrogens. So what we'd have is we'd have 2 carbons, which is 14, plus 1, 2, 3, 6 hydrogens. That's just 6 times 1. Plus an oxygen could be about 16. That's approximately equal to, I believe, 50. This gives us 28. This gives us 22. So it's about 50. Versus water, the molecular weight is going to be grams per mole or kilograms per kilomole, and the molecular weight of water is just 18. So what we would do is if we assume a 100 mole basis, you can say 100 times our 0.2. It's going to give us, so we have 20 moles of ethanol. So if we have 20 moles of ethanol, we then know that we have 80 moles of water. If we take this 80 moles times 18, we get 1,440 grams. So our total mass of this solution is 1,000 grams plus 1,440 grams from ethanol and from water, which is equal to 2,440 grams. So to figure out the weight % of ethanol, we take our 1,000 grams that we have of ethanol and then divide it by 2,440 to give us our weight % of approximately 40 weight % ethanol. Okay. If you have any questions with that, please feel free to reach out. We're essentially just going from mole fraction to weight fraction. So that allows us to then come here onto our enthalpy diagram and figure out what our enthalpies are so that we can plug in for our feed line. So again, we have Q is equal to vapor enthalpy minus feed enthalpy over saturated vapor enthalpy over saturated liquid enthalpy. So these are all in terms of composition of the feed, so they're all going to be just different locations for our 0.4. We know that the temperature is about 26 degrees C. So if we come up here, and we hit the 20, just a little bit above the 20, and then we go to the right, we can say that our enthalpy for our little hf is approximately equal, if we say that's about 50, we can say that that's close to 20-ish, 20 or so. And then for our big enthalpy, we go at the same spot. I guess maybe we'll try with our little h first. Our little h is our saturation at this enthalpy composition. So we come up to here, and we hit this line, and we go off to the right, and we say that's approximately going to be about maybe 80 or so. So we can say our little h is approximately 80, and then our big H is going to be approximately, we take our 40% composition, go all the way up to the top here, bring that across. We say that that's approximately 470, 480, so we say 475 or so. So then we can take our Q value, and we can say Q is equal to 475 minus the enthalpy of our feed is 20 over 475 minus the enthalpy of our little h was 80. So we can say our Q is approximately equal to 1.15 or so. Okay. The whole point of that was to allow us to determine what our Q line is going to be right here. So we can then plug that in for Q, which we said was 1.15. 1.15 divided by 1.15 minus 1 is going to just get us 0.15 times our x plus 1 over, this is going to be a negative 0.15 times our ZF, which is equal to 0.2. And this gives us that our feed line is equal to, so once we have our feed line, we can then plot that as well, and we can determine, at this point we can plot two of the three operating lines, and we can connect the bottom operating line to the optimum location, which I'll show in a bit. However, you just want to note that you can go in and plug these values in. Since we have our x, b, x, z, and now we have our q, we can plug into here and figure out our L over v and solve mathematically how to get our bottom operating line. However, this takes a lot of time. It's easy to do with a computer calculation, but if you're looking at graph, then it requires, and there's a much simpler approach which I'll show right now. So in order to actually plot the operating lines, what you need to do is you need to have your graph of your vapor-liquid equilibrium curve and the equations that you derived. So in doing this, I want to also note that y equals x equals xd or xb or x or z is always going to be a solution, and I'll show that right now. So if you take your x value here and you let that equal xd, this gets you y is equal to L over v times xd plus d over v xd. By combining, you get L over v. This is over v as well, so that equals plus d times our xd value. Again, from up here, we say that v is equal to d plus L, so we get y is equal to v over v xd, which just shows that y is equal to xd. So for our top operating line, we can always have a point on the y equals x line, which is your xd, okay? So the x value would be xd, and the y value would be xd as well. So to plot that, you can do your y equals x line here, like that. And then you can go to your x decomposition. So in this case, our x decomposition was 0.8. So we can go to 0.8 here and 0.8 over there and say there's one on the line. There's one dot on the lines. So to figure out the other point that we can plot, we can either use slope or we can use our intercept. If we use the intercept, that's just when x is equal to 0. So we can say y is equal to, this term goes away, because at this x is 0, of 0.375 times our x decomposition, which is 0.8. So the corresponding value to that, or our y-intercept value then, would be equal to 0.3. So the other point that we would then have here is, it's our intercept, right? So it would be right here. So we can draw a line for our top operating line and say it comes here. It goes to 0.3. So that's going to be our top operating line that we plotted, using just the intercept and the y equals x equals d line. Okay. The next thing we want to use is our feed line. So to plot our feed line, again, we can make the case that our y equals x equals zf is a solution to the point. So what we can do is we can go to, if our z is equal to 0.2, you would go to 0.2, and that's your point. From here you can use slope, or you can plug in another point and solve from there. So if I say I wanted the point at 0.3, so let's say y of x equals 0.3 is equal to 7.67 times 0.3 minus 1.33 would give us the corresponding value of 0.97. So I would have to go from 0.3 to 0.97, which is about here. So I can then plot a line from there. Say if I go from here to right here, that is our, okay? So from there, we have our bottom operating line, which is over here. We know, again, we can also say that the solution to y is the solution to x when x is equal to xb. You can derive that by letting this equal xb and subbing in solving, you get the solution that you also cross the y equals x line at your x bottom composition, which our x bottom composition was 0.02. So we would say is one of the points on this graph is 0.02, which corresponds to right here. What you can then do from there is you can, you know for this one that the optimum location is going to be where it intersects at this point right here. So you can go in, you can solve, since you have your Q value that we solved for, you can plug in for this equation. You have your L naught over D, which is your reflux ratio that's given. You have your Z, XB. You can plug in and figure out your L bar over V and solve from there. Or you can say, because this problem says that the feed is entered inside the optimum tray, you can connect these dots together and say that our bottom operating line will be here. Out there. So now we have our McCabe-Thiele diagram. What I'm going to do right now is just clean it up a little bit so it looks a little bit nicer. So all I did was I reduced some of the lines here, made it smaller, so that it's a much nicer graph to look at. So when you are doing your McCabe-Thiele diagram, here's the point where when you have the operating lines plotted, you can then do the stages. So we'll do that now. Go across and down. You're going to want to make right angles here. For the sake of this problem, I'm just going to go relatively quickly. But please draw straight lines when you are doing this on homework and exams. Now right here, I want to illustrate that we're going to come down. We're crossing the feed line at this point. So this is where if we actually project the feed line further out, this is the stage in which we are entering the feed line. So again, we drop from our top operating red line down to our bottom operating green line, and we keep going from there. Now here's where you want to notice that as you are approaching your bottom concentration right here, when you cross that line, that's technically where you've accomplished and you have achieved the separation, but you want to keep going because you can't have a fraction of the tray. So at this point you can do that. It's about a half or 3/4. You can take the approximation of how much of that tray is, but we're not going to do fractions of trays, so we're just going to want to say it's a whole tray. So now comes the part of numbering your McCabe-Thiele diagram. So important note is to go back and see what are you using. So you are using a partial reboiler and a total condenser. So since you're using a partial reboiler and a total condenser, the last equilibrium stage is going to be your partial reboiler. So we have this is 1 stage, 2, 3, 4, 5, 6, 7, 8, 9, and 10 equilibrium contacts. However, this 10th equilibrium contact is your partial reboiler. So what you can say is number of stages needed is you need 10 equilibrium contacts. What you can also say is that you would say you need 9 trays plus 1 partial reboiler. So that would be your answer to how many trays are needed. The other question was, what feed location does it go into? And you see here that it's going into the 8th tray. So you would say the feed into 8th tray, 8th tray from the top would be your answer for which tray locations should the feed tray be in. Now note that this is a different answer than the book. The reason being is because I did it really quick right here. I did not go take my time and make straight edges. However, if you do that, you should be able to get a better approximation, closer to the book, more exact answer. In addition, the Q value that we got here is very different. So the slope of our feed line is very different because this is an approximation that we get from the enthalpy charts. If you were doing an exact calculation, which is preferred, you would be able to get a more exact, better answer. So that is it for the first part of the problem, where it asks for that's what this problem asked for specifically, was the total number of equilibrium trays and the feed location. But what we can do is we can take a step further and figure out what is the energy requirements around the heater and around the reboiler. So to do that, if we have where this is our partial reboiler, from the energy balance, we have, as far as going in, we have the feed coming in times the enthalpy of the feed plus the duty about the reboiler plus the duty about the condenser. It has to be equal to the distillate flow rate times the enthalpy of our distillate plus the bottom flow rate times the enthalpy of our bottoms. In order to figure out these enthalpy values, we need to use this enthalpy chart. However, note that the enthalpy chart is in weight fractions. We have our enthalpy weight fraction of our HF, but we need to go back and figure out our enthalpy weight fractions for our distillate and our bottoms composition. So right here, I went ahead and did the work for determining what the weight percent is going to be for our distillate and our bottom. So we end up having that our distillate is that, and our bottom composition is that. So if we're looking at, let's let red be our feed enthalpy, which we already figured out. Our feed enthalpy is going to be what we did previously up here, which is approximately 20. So we can say our enthalpy from our feed is approximately equal to 20 kilocal per kilogram. Our enthalpy, if we say for XD, so we have the statement says that this is returning reflux as a saturated liquid. That means our distillate must also be coming as a saturated liquid as well. So we go to our 0.92, which is just a little bit outside of our 0.9, and we go to the saturated liquid range, and it's right there approximately. So we would say that that's approximately 55. So our enthalpy for our distillate is approximately 55. So if we use purple for our bottom, we just go to where our weight fraction is approximately 0.05. So 0.05 is approximately here, and that is a saturated liquid as well. So go here, so it's about, we can rule that about 99. So we would say that our H bottom composition is approximately 99, and it's the same units, cal per kilogram. So at this point, we have this, and this. Although we have our flow rates, distillate and bottoms in terms of mole per hour, but it's easy enough to figure out how to do it in terms of weight. So we can do that in the next step. I'll do it for our feed, and then you all can do it for your distillate and your bottom composition. So for our feed, we know that our feed is equal to a 1,000 kilomole per hour, and we have that the fraction of ethanol is equal to 0.2 mole percent. So if we want to figure out our flow rate, we know that the average, we could figure out our average molecular weight of the system. So we would say we have 0.2 times the molecular weight of ethanol plus 0.8 times the molecular weight of water would be our average molecular weight of this system. So we can say 0.2 times 50 grams per mole plus 0.8 times 18 grams per mole, and that would end up giving us the average molecular weight of approximately 24.4, this would be grams per mole. And if we have the flow rate of 1,000 kilomoles per hour, then we can multiply that by our 24.4. This can be kilograms per kilomole. So we can say that the total flow rate then is equal to about 24,000 kilograms per kilomole. Okay, and then from there, because we have the weight fractions of our distillate and our bottom compositions, we can figure out our D and B in terms of mass flow rate. So if we take our overall again, this is our D, this is our B, this is our feed. We have our feed weight fraction calculated previously, so we know that. I just showed that we have the calculation for our XD in terms of weight percent, and we have our XB in terms of weight percent already as well. We can do and now we just have our feed in terms of kilograms per kilomole. We can then do an overall balance, F equals B plus D, and we can do a most volatile component balance in terms of our weight fraction to give us what our flow rates of B and D are in weight fraction percentage, XD in weight percent plus DXD in weight percent. Okay, so that's easy enough. We'll be able to figure out B and D at this point. B, D. So at this point we have everything except for our duty around either the condenser or the boiler. Because we have a total condenser, it's going to make it easier to do it off of the balance around the condenser. So if we say that we have our vapor stream coming in, and then our condenser, and then our condenser splits into liquid and distillate, doing an energy balance, we'll say that vapor times the enthalpy of that vapor plus the duty required by this is an energy balance. The duty about the condenser is equal to the enthalpy leaving, L times, this is liquid, so it's little HL, plus the distillate flow rate times our XD. I'm sorry, it's not XD, it's HD. And by rearranging, we can say that the duty around the condenser is equal to negative V big H, HV plus L little HL plus D HD. Here's where we need to look at the overall mass balance about this. If we look at that mass balance, we know that V is equal to V is equal to L plus D. We're also at this point given the reflux ratio of L over D is equal to, I believe it was 5/3. So we have that ratio if we need it. So another thing to note is the enthalpies here, the enthalpy for our liquid and the enthalpy for our distillate are the same. They're the same because what we're doing, if we look over here at this drawing, we're taking the same liquid stream and we're just splitting it. So the enthalpies are going to be the same because we're coming from the same stream. So by letting those be the same, we can say that our Q is equal to negative V HV plus L plus D times just our little enthalpy because it's going to be the same composition, same saturated liquid, HD. At this point, we know here L plus D is equal to V, so we can say that this then further simplifies to get minus V big HV plus V times HD, which then we can factor. So when we go ahead and factor this out, we can leave the negative out and bring the V. We get that V times our HD minus our big HV. And that's going to be the duty around the condenser. So to figure out what HD is, we already figured that out, the liquid composition previously. So we would have to just figure out what our HV is, which is the exact same weight fraction that we're doing here of this 92 weight fraction. we just go up to the saturated vapor line. So we would go here, we go across, and we say that's approximately, we could say 280. So then we can figure out our duty around the condenser, because now we would have our HV. So our HV would be equal to approximately 280. So if we rewrite this, Q condenser is equal to V times HD minus HV, where we would need to then find our V. So we can do that because of these relationships that we have right here. We know that V then has to be equal to, if we rearrange this, our L becomes equal to 5/3 D. By plugging that into here, we get that our V is equal to 5/3 D plus D, which is equal to 8/3 D. And at this point, we have our distillate flow rate already. So we can figure out what our V is, and we can plug it in and say this is just equal to 8/3 times our distillate flow rate times our H little d minus our HV. And at that point, we would have the duty around the condenser because we have all those values. Okay? Once we have our duty around the condenser, we can then plug it here. We can then rearrange and say that the duty around the boiler is equal to this. And then we would have all these values already given. These are from the enthalpy charts, the enthalpy, and these values are from the overall balance that we did in terms of mass instead of molar flow rate that we converted and showed here and here. Okay, at that point, it's just plug and chug, make sure that you don't mess up your calculations. If anybody has any questions, please feel free to reach out to me. Otherwise, I'll see you all on Wednesday.